Good evening everyone. It's Wednesday night, it's Physics Rocks time, and tonight it is Lenses episode 2. We're going to take a look at diverging lenses, how they work and how they make virtual images. We're then going to move on to the uses of lenses in terms of cameras and projectors, and then at that stage, if you're double award, you're good for the night, you get to walk off, but if you're triple award, you get to hang around for figuring out how we fix long sight and short sight. Alright, so let's get cracking at now because we've got quite a lot to cover. Right, so your basic diverging lens looks a little bit like this. Okay, it's got a flat top and it bows in, so it's thinner at the center than it is at the top. Alright, now in terms of basic understanding of that, similar to our lesson 2 weeks ago where we looked at a convex lens as being essentially two prisms, one up and one down, we can look at a concave lens, which is what this is, as being essentially two triangles stacked on top of each other, but like this. Okay, and in this case, we can again apply our general rules of light to it. That if I have a ray of light coming traveling in here, and I'm going to put an arrow on that because it's a ray of light, I have a ray of light that strikes an object, and we should be getting sick of that sound now, so therefore I should draw a normal. So I'll need a dotted line that doesn't have any end styles or start styles, so we'll just change that up. Okay, so get that, and we draw a normal in like that, a normal 90-degree line to the point where it strikes. Okay, now we're traveling from a less dense material out here, which is air, into a more dense material. Okay, so I'm going to slow down and I'm going to bend towards the normal. So as I travel this way, going closer to the normal is like this. Okay, the angle gets smaller, so I end up with a traveling path like this. And I should put an arrow on that for the ray of light, but I'm going to leave it out for the sake of keeping it clear. I don't want a whole pile of random stuff going in there. Again, I've got a ray of light striking a boundary between two objects, so again I draw a normal in, which will look like that. And on the way out of here, I'm therefore going to have to speed up and bend away from the normal. So I was going to go this way, I need to get further from the normal, so I can't go this way, I have to go like that. Okay, so my ray of light that was parallel here, nice and horizontal as I've drawn it, ends up bent upwards and upwards again. Right, the exact opposite happens at the bottom here. We come in and we'll quickly draw our normals just to show you what's going on. So grab this dotted line and copy it. Okay, normal 90 degrees to the point at which the ray of light strikes, so somewhere like that. It's pretty close to 90, it's not exactly right, but right on the point where the light hits. Okay, I need to slow down and bend towards normal, so I was going over there. Let's get closer to the normal, so that's like that. And the same again on the other end. I need to then draw another normal, so copy that, bring it across, set my normal down. Right, and on my way out, I was going to go straight on, but I have to get further away from normal, so I can't go like this, I have to go like this. Alright, and what I've got is I have two rays of light that were coming in parallel to each other, are now coming out, and they are now diverging from each other, they're heading away from each other. A ray of light that comes straight through the middle travels straight on because it's sufficiently thin, there's actually no glass there. At this point here it comes in, but the normal is actually dotting along this because this bit here is flat. Okay, so exactly the same thing, so as it travels to the center of the lens, just travels straight on. Okay, so the result is that we have three rays of light that came in parallel to each other and now they're divergent from each other. And this is the standard kind of parallel light diagram for a concave lens. Right, now you don't draw it as two triangles, you then have to transpose that idea onto this diagram, but it's exactly the same concept. The ray of light comes in and then you don't really bother with what goes on inside it, you just go right, it comes out like that, comes in, comes out like that, goes in and comes out like that. So we end up with divergent light. Okay, but again, the process, the actual physical manifestation of what's happening there is refraction. It's nothing any more complicated than that. This is not any new physics. This is exactly the same as what happens in your glass block experiment from maybe like 2 months ago. It's just set up differently. Okay. Right, so what we have then is we have a situation where we need to label this just like we did with our previous concave lens. Like we still have an optical center, we're still going to have a focal point, but it's going to be slightly different because the focal point is not the point where parallel rays of light are brought to focus, because parallel rays of light are not brought to focus in this thing. Okay, the object at infinity never gets seen as a sharp object in a diverging lens. So we're going to have to do a little bit of jiggery pokery. That's not really a word, but we're going to use that to figure out what's going on here. So let's take our standard kind of setup, our F2F kind of system, and we'll bring that onto a new page so I can copy and paste it when I need new ones. Okay, so first difference is that when you're drawing these out in graph form, a concave lens is drawn like this, with the arrowhead pointing inwards, and that's to show that it's thicker at the ends here, and then it thins down into the middle. So this is to show kind of the ends of the lens. All right, so let's imagine that we have parallel rays of light. So getting this down into diagram form. So there are two parallel rays of light, and they are going to be divergent. And we want to figure out like where they're diverging to. We don't just want to draw random lines. Like I could draw that, I could draw that, I could draw that. Which is it? Okay, so I've been given F, 2F, and whatever's going on here. Now the cool thing about parallel or about divergent rays of light or diverging lenses is that their focal length is described as the point that parallel light appears to have come from once it's passed through the lens. Okay, so I'll say that again. It's the point through which light appears to have come from after it passes through the lens. Okay, so let's imagine that we have an observer over at this side. So let's draw a gigantic eyeball in here. Okay, so somebody's watching what's going on here, and what they see is two rays of light come through the lens. But what actually happens is this ray of light diverges outwards. I'm going to bring this eyeball a bit closer, in such a way that it looks like it came from F, like this. And this ray of light diverges outwards, making it look as if it came from F as well. Okay, so parallel rays of light that are parallel to the principal axis. Okay, so these are your rays from infinity. Make it look as if they came from the focal point F. Okay, I'm going to bring my eyeball a bit closer so that this guy can actually see what's going on. Or girl, let's not be sexist here. So there we go. So if somebody sees that, then their brain goes, all right, there's two divergent rays of light. Where did they come from? And your brain will track them back and go, right, well, light travels in straight lines, so that came from there, and that came from there. So if we're defining the focal point for a diverging lens, the focal point is the point from which rays parallel to the principal axis, keyword here, appear to have come from. Alright, that's important. They're imaginary. You notice there's no arrows on them. They're not really there. They're just like the mirror problem that we had ages ago. Alright, so what does that mean in real life? Well, what that means is that if I have an actual object and I want to take a look at it through a divergent lens, okay, so again, we're looking at a concave lens, divergent lens, like this. Yes, this is, thanks Doomsday 2.0, this is concave lenses, you're absolutely right. Just seeing a few people in the chat now. I was getting worried I was all by myself. Okay, so let's put ourselves a little object here. So we'll get an arrowhead. Arrowheads are always good because then we can tell where the top and the bottom is. And we'll do it on both sides. Though normally you don't get that. Normally you're never asked to find one point, but we'll do both. Alright, so two rules again. Rule one is the rays of light that we're interested in are ray one, the one that travels through the optical center, is again undeviated. Just like in our convex lens. That's a rule for lenses just in general. If a ray travels through the optical center, it is undeviated. So we can go, right, that ray definitely exists. Okay, another ray that comes from the top. Remember, there are billions of rays coming from the top going in all sorts of directions. We're only interested in two of them, the one through the optical center and the one that travels parallel to the principal axis. This one here appears, critical word, appears to have come from F. So we draw a dotted line back, like that. Okay, where does it go on to? Well, it goes on to appear as if that bit there that I'm running my cursor along is a straight line. Okay. Now, an observer has to be here. Has to be able to get those two rays of light into their eye. So they're on this side of the lens. They have to be looking through the lens at the object to be able to see what's going on here. This is not like a projector. This is not like a convex lens where it's making a real image. Your eyeball position matters. Okay, so the point that was the tip of your arrow here is now located here. Okay, so that's my tip to tip. Now let's go and change our color and do the bottom end as well. So get some blue out. Parallel to the principal axis. Looks like it came from F. So again, looks like it came from F, so it's going to go out that way. It's going to travel straight on, like that. Okay, just about being accommodated by my eyeball. It's not too bad. Little arrow there, make sure we don't forget that. And a ray of light that travels through the optical center, like that. And the crossing point there, when that goes into your eye will position those two things as being down here. And I'll do that in blue so that we see the difference. Alright, so my new image, or my new object, is going to be here. There's the top, and there's the bottom. So my new object is going to be created here. So my original one was there. My image of that is going to be created here. It's going to be moved. Alright? Happy? So what we end up with is a different type of image. And what are the properties of this image? Okay, what can we say about it? Well, we can say that it's upright. Unlike most of the other ones that were done on convex lenses, they were inverted. This one is actually upright. It's diminished in this case, so it's smaller. It's closer to the lens. It's been moved from between F and 2F. It's been moved closer to F. And then finally, it is virtual. Okay, no actual rays of light cross through this. Now one does, there's one real ray, but the second one, the one that actually positions it as your for your eye, is not a real ray of light, and as a result what's being created is not really there. Okay, so it's upright, diminished, closer to the lens, and virtual. And as we'll discover a little bit later on, this is how you correct people that are short-sighted, because this is bringing a large or a distant object closer. And that's what short-sighted people can't do. They can't see far away stuff. So you bring the far away object closer to them. Yeah. Okay. Not quite a microscope lens doomsday because the object isn't getting magnified. But yeah, you know, it's a good idea to be able to use this and bring it closer. Right. So this is your divergent lens. Happy? Hope so. All right. So all you need to be able to do is reproduce this diagram. Likelihood is you don't need to do the blue bits. Normally it'll just be sat on the line, so you'll just have to find the top of it, and then the bottom of it will be on the principal axis again. Alright, so moving on to the uses of this. Like, what are the uses of lenses? Why do we bother with them? Well, you actually don't need to know any uses of concave lenses besides the fact that they're good for sorting out people's short sight. And we'll come to that later on for the triple award. For double award, you just need to know it helps sort out short sight. Right, for everybody else, you need to know two convex lens situations, which is that of the projector and the camera. Okay, so what you have in a camera is you have a convex lens, and once again you have, you know, principal axis like that. I'm going to try and fade these out a bit, make them a little bit smaller because we don't want them to get in the way with the actual diagram, but we'll make them dotty, but they're still there. Okay, you got your principal axis and you're kind of vertically through your lens like that. And you have a focal length again, and we'll put that somewhere around about here, just for the sake of it. Quite a short focal length. And what we want to do is somewhere back here, we want to have some form of photographic film. Back in the old days, photographic film. These days, probably some form of photo detecting sensors in a digital camera or in your phone or on something like that. There's some form of photo sensor that can make sense of the light that's coming through it. And the idea is that you take something like a tree that's a long distance away, like that's not a tree, that's not even close to a tree, but if we colour it in we can pretend it is. And there's some green leafy bits and some brown barky bits. Yeah, lovely, tree. It's a tree, alright. And then what we want to do is we want to take this object and we want to put it onto this. Okay, this object is is further away than f. It's well beyond 2f. So what we want to do is we want to produce it onto here. So we take a look at what happens. Take a ray of light parallel to the principal axis, gets refracted through f, like that. Okay, so that's the top of our object. And then the same one travels through the optical center and ends up here, like this. Okay, so the perfect place to put my photographic film is here, right? That's it, perfectly in focus. Now obviously I can't move my photographic film, but what I could do is move my lens forward and backwards until I get that right. And that's what you're doing when you're zooming or when you're adjusting the lens on something to get a nice sharp picture. Sometimes it's out of focus. When you're focusing, what you're doing is you're moving the lens forwards and backwards so that you're getting the right distance to whatever your photo thing is. Okay, happy? And then at the bottom of the object, you then go, right, okay, bottom, parallel to the principal axis, up through F, like that, and then straight through O, and it should kind of bang right there. Okay, that's a horribly complicated diagram, but what you should realize is the bottom of your object ends up at the top of your image, the top of your image, or your top of your object ends up at the bottom of your image. But more importantly, what was a very big tree ends up as a very small picture, because an object beyond 2f for me becomes inverted, real, but diminished. And this is how a camera works. Right? Happy? Good. Okay, so cameras use this. Now, in an exam, there's a lot of bump that goes along with that. Okay, you end up with, you know, some form of little picture of a camera that you get, like here's a big lens, and like there's the focusing tube bit, and then you try and make it into a camera-y shape like that, and then somebody who's still living in 1978 like draws in photographic film for you and puts in a couple of reels, and you're 16 and you've no idea what the heck this is, but this is an old-fashioned camera. Ignore it. It's got nothing to do with anything. The physics that's going on is there's your principal axis, there's your vertical, where's F, and we need to find how we get a sharp focused image on here. Okay, so parallel to the principal axis, forced through F, wherever F happens to be on here. Top of the object through O, bang, meets there. Okay, so F's probably not there. F would have to be like there. And if I wanted to find where F was, if my object was there, my focal length would have to be this, because anything other than this, I'm not going to get a nice sharp image. So I could use that to find F. Good. I'm glad you like physics, Doomsday. That's good. That's good. But watch the language, guys, especially stuff that has profanities in it. It just gets auto kind of corrected out. Alright, so that's the camera. The projector, on the other hand, is basically the opposite. Okay, so what you do, again, a projector uses a convex lens. So you get a convex lens like this. Alright, and again, you draw in your principal axis, you draw in your vertical through your points like this. In fact, you don't even really need to bother drawing the lens. Like this is enough. And then what you want to do is you want to note where F and 2F are. Now, this needs to be a little bit more precise, so we'll measure that out. So that's the distance to F that I've invented. So that's got to be F on the other side. Don't worry, I'll take out these dotted lines in a second. And then over here, this is 2F on this side. Okay, I'm not too worried where 2F is on the other side. Okay, so there's F, and there's 2F. And what you use for a projector is you use the fact that between F and 2F, you end up with a magnified image that's real. Okay, closer than F, you end up with a magnified image that's virtual. That's no use. Okay, we need a real image, because there's no point like having an optical illusion in a room that everybody has to look through a lens to look at. Right, so what I do, again, I play the same game, parallel to the principal axis, pushed through F on the other side, through the optical center, undeviated. Okay, and there's the top of my new image, or the top of my image position. It's a real position because it's two real rays of light arriving there, and what I see is I end up with a magnified image. All right, and if I move F in even closer and closer and closer, this gets bigger and bigger and bigger and bigger and bigger. Right, so I end up with an object that gets, or with an image that gets further away and gets bigger all the time. And this is how projectors work. A projector takes a picture, usually done by some form of like crystal or things like that there, or LCD screen or some form of circuitry. It used to be that you put a slide in and you shone light behind it. Now it's done with like colour wheels and all sorts of things. You don't need to know anything about that. You just know you get a picture that's bright, you shine it through a lens, and it ends up coming out on the other side bigger and real. And it's because of the fact that your object, your lit up thing that you want it to project, is between f and 2f. Construction wise then, again, you end up with a weird little picturey thing where you go, right, there's my lens, here's f. Oh, need a different picture here. So here's f, here's 2f there. So f on the other side is like here, principal axis, don't even bother drawing it in, and then you'll have the picture that you want to make. Right, and that's all contained inside a box. So the lens, you'll have seen this in your classrooms, I'm assuming, if you go to school, that the front of a projector looks like this. There's a big lens at the front, and then bring that to the front. Okay, so you got that. And what's happening is that the ray of light comes out, hits the lens, and is diverted through f, and then the other one comes through the optical center, which is like around there, and you end up with a big arrow on a screen far away, like that. Job done. Everything else, window. Is that alright? Hello, Vladimir Lenin. Nice to see you. And that's it. And if you do double award, that's you for the evening, really. That's all you have to be aware of. 2 uses of convex, well, 3 uses. The one was the magnifying glass. Check that out in episode 1 from last week, or 2 weeks ago even. So we've got magnifying glass as a use for convex lenses. We've got back here, we've got a regular camera, making a faraway object look smaller because it's beyond 2f. We've got a projector, object between f and 2f, making a projected larger image further away. Right. That's it. Divergent lenses, okay, that's your concave lens. Useful makes a virtual diminished image that's closer, useful for people who have short sight. If you're doing double award, you're done for the evening. Feel good. Check out the little link in the description below that's got a worksheet in this. Have a crack at that and properly feel good about yourself. Triple award though, you need to hang around a bit because we're going to talk about people's messed up eyesight. Alright, so first things first, let's see about what's going on in your eye. So your eyeball is a bit like that. It's like a big, like a rugby ball shape with what's essentially a convex lens sat there. Okay, since this is made of fluid, this bit acts like a lens as well, but we're only going to consider what really happens in here. We're going to simplify it a little bit. Okay, so normally what happens with a normal human being is that light that comes from an infinitely large distance away, so that's like multiple meters, remember, like infinity is not infinity where that comes, but parallel light comes in and gets focused onto your retina like that. It's all good. It's all good. And as the object gets closer and closer and closer, that becomes a slightly more tricky task. So we've got like a little dot here, for example. Those rays of light are going to be diverging, coming into your eye. But again, your eye's lens brings them back into focus so that they hit a single cell or single group of cells back here. They're focused at a point. Your brain can make sense of that and works out that that's a single point. Therefore, that becomes a single point. Easy. Hopefully no one's talking because everybody's listening. And that's what the normal human being can do. And you can do that actually for distances, like basically until you can't see any more stuff because the detail's gone and there's not enough light. All the way up to about 25 centimeters is about the closest that the human eye is supposed to be able to do this comfortably. All right. But not everybody is created equal. And there are some people that suffer from short sight. Okay, short sight, sometimes called myopia. You don't need to know that, but it's a cool word, and it's a good word to use in English essays. If somebody's being short-sighted, they're being myopic. Use that in your English teacher; they'll be like properly impressed. And the problem with a person who has short sight is close-up objects not a problem. In fact, we short-sighted people, I'm in that group, have superpowers when it comes to being able to see stuff close up. We can yeah, no bother, 10 centimeters away, I will take care of that. The problem is anything beyond, maybe a couple of meters even for the best of us is a big problem. And certainly anything at infinity is an issue. So when parallel rays of light come in to a short-sighted person's eyeball, this happens. Okay, the rays of light get converged too quickly. Okay, they get converged too soon. They're supposed to converge back here. They're being converged here. And there's no light-sensitive cells here. There's no retina here for you to see. So what you see at the back here is a bit of a problem because this ray of light should have been a single point and it's making multiple points on the back of your eye, and that's going to cause blurriness because instead of getting one sharp image, you're getting multiple images overlaid on top of each other, and therefore it gets blurry. Okay, imagine stacking the same picture. Imagine having a picture on like acetate, like on see-through plastic, and you've drawn a little picture and you've photocopied it like 100 times, and you lay them ever so slightly one over the other, over the other, over the other. In fact, I might be able to do that here to show you what I'm doing. Oops, wrong button. Okay, so if I copy that and 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 copy that, like really rapidly, even if I try and put this on top of itself, right? So if I put it here, right, you can see that I'm starting to lose the detail. And if I put more and more and more of them on top of each other, I start to lose what's going on. And you're getting a sense now of what it's like to be short-sighted, that you can see the general shape of what's going on, but the detail of my lens is gone. The detail of where that hits is gone. You're just getting multiple images laid over each other, all slightly out of position. Okay, and that's why you can't make out the details in people's faces and why you can't read signs at distance. Right, now, there's two possible reasons for this. Reason one is it's physical and that your eyeball is too long. And that's most likely the case. Alternatively, the way I like to think of it is that your lens is too powerful. Okay, your lens is overly converging light, and as a result, it's making a problem for you. Okay? I'm getting to it, mate. I'm getting to it, Ishmael. Okay, so your lens is either too powerful or your eyeball's too long. So we need to correct that. So if you've got too powerful a lens, what you need to do for objects that are far away for this short-sighted person is to make life more difficult for your lens. You've got to make it harder for that lens to work. So what we're going to do is we're going to pop back to the first page and we're going to grab my diverging lens. Okay, I'm going to stick it in front. Would have been useful if I'd actually pressed the copy button, but we'll go back and get it again. Copy. If this doesn't paste, I'm going to erase it. Paste. Good. Whack that in there and send that to the back so that my rays of light come over it. Now, parallel rays of light, when they're coming through a concave lens, end up diverged. Alright, so when they come in here, they get forced outwards. I need to make my lens a bit bigger, but that's okay. Alright, so instead of being nice and close together, when they arrive at my eyeball lens, they're further away than they should be from each other. So my eyeball lens has to do more work. That takes longer for it to focus, and as a result, my focal point is moved backwards a bit. And if I get the lens right, and I get the strength of the lens right, and I get the divergence right on it, then what I end up with, I'll make these blue, otherwise that's misleading. What I end up with is I end up producing a nice sharp focused image on the back. Alright? Happy? Now, the issue with this is that solves the short-sighted person's problem with far away objects, but unfortunately it takes away their superpower of being able to see stuff really close up. That's not a big deal, to be honest, because most things don't happen at 25 centimeters away from your face anyway. So you go from being able to see 10 centimeters away to being able to see 25 centimeters away, and nobody cares about that. So most short-sighted people wear their glasses all the time. Long-sighted people, on the other hand, have the exact opposite problem. Long-sighted people have no problem whatsoever with objects that are a long way away. So let's get their eyeball in. So there's a long-sighted eyeball. We'll make the lens big to start with in this one. Okay, and they have no issue. Far away objects from infinity, focused as they should be. No problem. Their problem arises with close-up objects. So something like a little dot here. Their problem is that the normal person's eye at 25 centimeters, they considered to be perfect distance. Okay, a normal person's eye just does that. That's great. Unfortunately, for a long-sighted person, their eye doesn't get the light converged in time. They get that. Okay, their convergence point is a little bit behind where the actual back of your eye is. Okay, their convergence point's back here somewhere. This results in the exact same problem as short-sighted people have. Right, that they have multiple image points being formed from one single point object. So again, they get this overlaying kind of lots of images on top of each other, and that ends up blurry. What's the problem here? Well, they have the exact opposite problem as short-sighted people. Their eyeball is too short. Or their lens is too weak. Okay, this is long sight. If you want to be super kind of cool about this is hypermetropia. Long sight. So their problem is that their lens is too weak. Their convex lens is not good enough. So in order to solve this, we actually stick another convex lens in front to give them a hand. Alright, so what happens then is, we'll do this in blue. This ray of light, instead of traveling straight on here, as it comes through this lens, gets converged a bit. And then when it arrives at this lens, the lens has less work to do. So it arrives here, as before, and gets converged a bit, and that makes life easy. Okay, and that allows our long-sighted person to see an object that's close up. Downside to this. Downside is that this allows our long-sighted person to see things that are close up easily, but it takes away their superpower of being able to see really long distances away. And that's bad. That's bad for a long-sighted person. So what happens is that the long-sighted person, they're the kind of elderly people. You know those people that look over the top of their glasses at you? They're long-sighted people. You know the little grannies that look down their nose to read, but then look up to talk to you? They've got long sight. What's happening with them is they need the glasses to see the book because it's like 26 centimeters away and that's hard for them to see. So they look through their glasses to see that. But you're like 3 meters away and their glasses stop them seeing far away. So they have to take the glasses off to look far away. And long sight is, generally speaking, a problem that's associated with age. Okay, so they're the people with reading glasses. Okay, you've heard of people with reading glasses. You've no idea what they are because you're young, but that's what reading glasses are. They're long sight people allowing you to see stuff close up. Okay, so correction of long sight, convex lens. Correction of short sight, concave lens. Why? Because short-sighted people, their lenses converging the light too soon. We need to make life more difficult for short-sighted people. Remember, life's difficult if you're short. Okay, so we need to make life more difficult for long-sighted people. You need to help them out. You need to help them out. All right. That's it, really. Nothing to it. We're 3 minutes over tonight, so thank you so much for hanging about and spending the time with me. Again, if you check in the description, there's a little worksheet for you to do and have a crack at it. If you're watching this not live, because I know there's a chemistry reset exam tomorrow, drop a comment if there's anything that you liked, didn't like, want to feedback, because I'm trying to make this better. This happens for you guys for year 12s every 2 weeks. If you're doing a year 11 module again as well, every week, because it goes 11, 12, 11, 12, 11, 12. So hit the subscribe button, hit the bell notification so that you get a reminder when I'm going live. And don't forget, everybody, physics rocks. It's true.